Hi guys, welcome back to Solar Engineering. So let's go and take a look at PV cells, right? If you're looking at a PV cell, you'll be looking at a current source, generally simulated by the PN junction hole pairs, would provide you with electron flow, would provide you with a current source. But we can't just look at it like a current source because we have to simulate it with essentially a diode in parallel with it, as well as a shunt resistance for leakage current, as well as a series resistance if we're being real for real world circumstances, because no material that we use has zero resistance except superconductors, and I mean they need ultra low temperatures, and it's just not feasible to have that right now in PV. So we model it like this, and the I is across the output, of course. All right, so if we short these two outputs together, we get ISC. If we leave them open, we get VOC. And when we have VOC, the RS is like kind of this RS here is kind of not even going to be like relevant in the equation. So if we're working back to that and there's no current flowing through it, it's just not really going to matter. But you guys are going to see what I mean now. Our output over here is equal to our current generated by a photovoltaic current source minus the diode current minus the shunt current, right? Which is essentially this, which is tiny. Now let's go and further break that down. So the shunt current will basically be broken down into Ohm's law. We determine this with Ohm's law. The diode current over here would essentially be broken down into this equation over here, and then the IPH would essentially stay IPH, right? So if we go look at this equation here in the middle, it's the only one that's really tricky, because if you go and look at the equation on the right-hand side, that's regular Ohm's law. On the left remains IPH, which is the current source that we have, right? So in the middle, we get this diode equation. Now, if we go look at the diode equation, indeed, the dark saturation current multiplied by your exponent to Q. Q is electron charge, 1.6 times 10 to the power minus 19 coulombs, right? Multiplied by voltage plus IRS. The reason you add the IRS at the end here is because the terminal voltage across the diode is higher than the output voltage. So you basically just take the current that you have at the output and you can multiply it with a series resistance, and then you can get the voltage across the diode, right? That part's not too hard to understand. Just understand why it is there. And then at the bottom, we have the ideality